Really? Okay. One of the talks, I didn't even spot it until I got there. It's 2 o'clock. 1 o'clock to 2 o'clock. 2 o'clock. He said, transient.
Hey.
Oh, okay. Sorry, you want the thumbnail. Are we using that computer?
Yeah.
That's why.
And so it's a self-resetting fuse. And maybe the arc suppression key ingredient.
So there are commercial devices that do the same thing.
Yeah, this is a little tiny.
Okay. Would it be useful too for line jumps?
That's exactly what I was thinking. I plan to get home this email to Dave Strobel and say, you know, make sure you talk to the boys.
Okay. I completely forgot about it. Is it happening tomorrow?
Yes, tomorrow.
Okay. I'll check.
How to find a habitable planet besides it.
Correct.
Or does that not count as habitable?
That counts.
Okay.
I occasionally ask optimists, is there another place in the solar system that's better, more habitable than the worst place on Earth other than in a volcano that's erupting at the time?
Right.
You know, Everest has much higher air pressure and temperature than the best places on Mars.
Or give the parameters to a bunch of modeling groups and see which ones call Earth habitable and which ones don't.
Yeah.
FunQ dongle is crossing the Atlantic.
You gave it to somebody?
No, I bought it from yesterday. They shipped via FedEx.
Okay.
Turned out the flight from Stansted to Memphis is FedEx 1. So it's on FedEx 1. Anyway,
You might find
pick up an
interest in
antenna
my
for your
latest
site,
paper,
so you should be able to listen to satellites.
I found that it's a Galilean
I recall
Galilean
they did a thing
transformation.
about FedEx truck to go to big wire across
It's rid of the paradox. You have a railroad station,
Yeah,
trains go
FedEx
this way.
double
with
trailer.
velocity, trains go
For some
this way.
reason crossed over into the bus.
Visit
I
the
was, when I went to
And the solution is synchronize.
I presume it's UCSD seminar?
Another type of workout transformation.
So, I've never heard anything about that.
That way you
Wonder if just the thing, you know, flying single engine plane, one pilot under all.
max speed.
Oh, should I use this or should I use?
It's up to you what you feel comfortable with. This is laser and
Okay, it's just two. Is that, doesn't matter.
whatever you are comfortable with.
It reminds me of the paradox, the aerial service.
It's in part because and then if
So
you
did
get
you
this.
see the email I sent yesterday?
You want to play it for a second? See if it-
I opened it up and haven't looked at it.
So you have the,
These
you have this as well over here.
different.
Okay.
Decided that I was going to
Perfect.
Okay.
I think that's where, and it's going to be an appendix.
You're here from Boston?
No.
You in Tufts?
What's Tufts? Yeah. I'm from Laguna Beach.
Oh, okay.
Yeah.
That for stuff.
Were your family still there?
My dad, well, he moved to Costa Mesa. My mom lives in France.
I'm very different.
Yeah, it's very nice. That's nice because I get to visit in Provence.
That was like when I went to Boston. My dad was in Connecticut.
Oregon.
A lot of the same there.
I never went over to Boston.
I
never went.
As long as it makes sense at all, it makes sense to.
Where are you from originally?
From
Buffalo.
So let me just suggest.
I've never been to Buffalo.
Cell
I
stuff.
say you're missing anything.
Yeah.
If you want, if you have like, I'm not sure how
There were no planets, so they're only brown dwarfs.
well, maybe we turn off the lights. He was fine though.
So we don't need that. We don't need the high contrast. Yeah, there are no high contrast.
Okay.
Okay. All right.
Okay, wow, a natural break in the conversation. That was great. It's my pleasure to introduce Dr. Brennan Bowler, who's coming to us from Caltech. Brennan is, are you the inaugural?
Inaugural JCPA.
Yeah, so Joint Center for Planetary Astronomy Fellow at Caltech. It's sort of a joint center to combine planetary astronomy and planetary, I guess, planets, solar planets, astronomy, and a little geophysics in there as well.
A little bit, yeah.
A little bit, okay. He just got, this is his first postdoc position. He graduated from University of Hawaii IFA in 2013, where he's working with Dr. Michael Liu, doing direct imaging of low mass, planetary companions to low mass stars, and particularly stars that planets you can actually resolve quite well, so you can start studying their atmospheres. So I'm not going to, well, this is not the topic of your talk, so I can.
It's a little bit.
Okay, it's a little bit of
it's
it.
good.
Okay.
It's all good.
So, so Brendan had a number of papers as a result of the thesis that really explored in detail the atmospheric properties of these things. It's a very rare population. It's very hard to separate out planetary atmospheres from the extreme glow of the host star. And his project was able to find, I think, 2 or 3, which triples the number.
Brown dwarfs.
Brown dwarfs,
yeah.
okay. So he's been a significant contributor to that sort of population and sort of further understanding of the actual physics of the atmospheres of these planetary mass objects. And today, and I should also mention he's won several awards for his PhD thesis as well, including the Trumpler Award from the not APS,
Astronomical Society
of the Pacific, yeah, ASD. So I'll let Brendan start his talk on outer architecture.
Thank you for that very nice introduction. So feel free to just interrupt me if you have questions. I'm happy to stop and just have a short conversation at any point. This can be relaxed and somewhat informal. But today I'll tell you about some of the statistical properties of the outer architectures of planetary systems that we know of from direct imaging. So when I talk about outer architectures, it'll be beyond about 10 AU. So not in any way touching the regime that we've been hearing a lot about with results from Kepler and RB planet searches for the past 15 or 20 years. So think outer architecture beyond 10 AU. And I just want to quickly acknowledge some of my principal collaborators, Michael Liu, Evgenia Shkolnik, and Motohide Tamura. So why do we care about direct imaging? There are 2 broad reasons. The first is that we can probe separations that are inaccessible to other techniques. So radial velocity and transit techniques, for example, probe much closer in. This is a comparison of the known directly imaged companions below roughly 80 Jupiter masses as of 2007 and 2014. Compared to the radial velocity detected population, which of course for RB detected planets, this is an M sin I, so it's a lower limit on the planet mass. And then of course the mass inferred from directly imaged companions is model dependent. But aside from those caveats, you can see that direct imaging has dramatically expanded the architecture of planetary systems to over 5 orders of magnitude. So from close in, we have hot Jupiters at less than about 0.01 AU, all the way out to beyond 1,000 AU. And now calling these objects planets might be a bit of a reach, but it shows that companions with masses, if they were detected much closer in, would be called planets. So regardless, it's expanded the architecture of what we know about. The second point is that we can characterize the atmospheres of exoplanets because we're detecting photons from them with this technique. So this is the prototypical example of a directly imaged planetary system, which we now know is actually very, very rare. This is the HR 8799 system, which contains 4 gas giant planets with separations between about 15 and 70 AU, and masses of about 5, 5, 5, or rather 5 Jupiter masses, 7, 7, and 7 Jupiter masses. So whatever formed these must have had been very massive, a very massive protoplanetary disk to be able to form essentially 40 Jupiter masses worth of planets. Now, again, we can characterize the atmospheres of these companions with high resolution or high contrast, low resolution spectroscopy. So we did this in 2010. We published a very narrowband spectrum of the outermost companion, HR 8799b. And already from this very narrowband spectrum, we found some really interesting results. What we expected to see in this K-band region at about 2.2 microns is a very deep absorption from methane, which is a temperature diagnostic and really the definition of T-dwarfs. So based on the luminosity and age of the HR 8799 system, we expected the planets to have temperatures of about 1,000 Kelvin. And at least for this outer one, we still think that that's the effective temperature, but there's something very interesting happening with it in its atmosphere, in its photosphere, to remove the spectral signature of methane. So that could be non-equilibrium chemistry. And now we have much better spectra, much broader spectra over the past few years. And there seems to be sort of a gravity dependency on the transition from L dwarfs to T dwarfs at very low gravities or very low masses. So this is a talk in and of itself. Lots of really interesting work being done. The problem is we only have a few directly imaged systems, so it's difficult to elaborate much more on that. But let me move on, and just to make sure we're on the same page, when you think direct imaging, you should think very young stars. So the younger, the better in general. And there are 2 reasons for that. This is the luminosity evolution of stars, which contract and heat up and release or convert gravitational potential energy into essentially heat and radiation, and they cool until they reach the main sequence, steadily burn hydrogen, and have essentially constant luminosities, at least for low-mass stars. Brown dwarfs simply contract and radiate their gravitational potential energy over time. The only difference in this mass definition of planets and brown dwarfs is the ability to burn deuterium, which accounts for this small bump in luminosity for brown dwarfs. Planets, on the other hand, simply cool over time. So if we want to image them, we should target stars where they're the youngest. So that's the first reason why we want young stars.
We're always seeing the self-radiation of the planet, never the reflected radiation off the star.
Right. In this case, this is all thermal emission, what we tend to observe in the infrared. So yeah, it's self-luminous.
As soon as the planet gets old.
Yeah, they pass through spectral types as brown dwarfs do. So M dwarfs, L dwarfs, T dwarfs, Y dwarfs.
Do the planets in our solar system lie on those curves there for planets?
Yeah, so let's see. Our solar system is 10 gigayears, so that's right here. And 1 Jupiter mass is here, so this should correspond to roughly 10 to the minus 9 luminosity, yeah. And if you convert this into temperature, too, the temperature, for example, of Jupiter is it's 130 or 180 Kelvin. I think 130. So it's sort of the goal of the field to some extent is to get down to a Jupiter and below that, at least with the current generation of telescopes and instrumentation. So I'll just mention that the second reason why we want young stars is that the relative contrast between stars and planets is much lower at young ages compared to older ages. So it's a contrast issue and a luminosity issue. So, of course, the youngest stars are in star-forming regions, the nearest of which are about 130 to 150 parsecs. So at 1 arcsecond, that corresponds to 130 or 150 AU. So that's not probing the physical scales that are ideal for direct imaging, or for directly imaging planets. On the other hand, the nearest stars are very old. 1 to 10 gigayears. They're very, the planets themselves are, have very low luminosities. They're essentially wide dwarfs at these ages. So the kind of compromise in both age and distance are these young moving groups, which have been known for about 15 years. And there's been sort of a revival in the past few years to identify new members. They're scattered throughout the entire sky, so they're difficult to actually find. If we had UVW kinematics, the distances and RVs for all of these members, then we could tag them to these groups along with age indicators precisely. But the point is that these young moving groups with distances of about 10 to 80 parsecs are sort of the ideal optimization scheme for directly image systems. So direct imaging has shown that these objects exist. So how do they form? There are sort of two flavors of formation or maybe migration. In this sort of in situ scenario, the objects, the companions, the planets that we image have formed where we find them today. So one possibility in this flavor is disk instability, in which very massive and very cold protoplanetary disks develop spiral instabilities, become tumor unstable, and collapse down to form gas giants. And models show that they can form planets with masses between about 1 to 10 Jupiter masses, so kind of in the regime that we're looking for with direct imaging. Cloud fragmentation is another possibility. In this scenario, giant planets at these sort of moderate separations are really the tail end of brown dwarf formation. If you have a giant molecular cloud, which develops a core and fragments to the opacity limit for fragmentation, which is a couple Jupiter masses, if they continue to accrete mass, they'll become stars. If they're formed in a non-hierarchical fashion, you can get a dynamical encounter that ejects one of these opacity-limited fragments to a wide separation. And so maybe this could account for some of the population of planets or planetary mass companions that we're finding today.
Why would these be companions? I guess because they're binary stars.
They could be completely ejected and ionized, or just fly out to a wide orbit, or fly out to a moderate orbit. It's at least a scenario that maybe could account for some of the population. And then we have planet-planet scattering. So we know that scattering itself is probably pretty common, both from Rossiter-McLaughlin measurements at small separations. So this is the spin, so the spin axis of the star, and then the measurement of the relative angle of a planet orbiting it. Many of the hot Jupiters that have been found have misaligned spin-orbit axes, which suggests some kind of dynamical process that can disrupt that instead of it being perpendicular as we might expect from its formation. And a lot of the radio velocity detected planets have high eccentricities, which also suggests some dynamical past. So perhaps planet-planet scattering, in which a lower mass component is flung out to a wide separation, could account for some of this population. So I just want to talk very briefly about what some of the actual testable predictions are of these ideas. For disk instability, at least, the frequency of gas giant planets is predicted to scale both with protostellar and protoplanetary disk mass. So basically, for more massive stars, which might have more massive protoplanetary disks, you'd expect more planets. Okay, that sort of makes sense. There might be, say, a bimodal distribution in gas giant planets with maybe a peak at a couple AU formed through core accretion beyond the snow line, and another peak maybe at tens of AU formed through this disk instability method. And there's also this sort of phrase, runts of the litter, which Caitlin Crowder coined in 2010, in which these gas giants form through disk instability. It turns out it's very difficult to keep them at these very low masses. They quickly accrete enough mass to become a brown dwarf or even a low-mass star. So in that sense, the planets or planetary mass companions that we might be finding, at least formed through disk instability, might be sort of the continuous tail end of stellar and brown dwarf formation.
How about metallicity? Should that be?
So I actually had metallicity on there before, and I erased it. So metallicity is a tricky scenario. You might think that the metallicities of companions formed through disk instability should share the metallicities of the host stars because they're formed from essentially the same gas and dust. But if it forms in a region where you have planetesimals and you have planetesimal bombardment for millions of years, you can actually increase the photospheric or atmospheric metallicities of gas giants, even formed through this method, not simply through core accretion. So I think it's a trickier situation than as I initially thought. Metallicity does, on the other hand, or is a prediction from fragmentation. So it should share, because you don't have, it might not be formed in the disk, and so you might not have planetesimals forming alongside with it. The metallicities of planets formed through, or planetary mass companions formed in this fashion, should be consistent, at least with those stars. And of course, it's difficult to measure metallicities of giant planets, not just in our solar system, but outside of it. So, but this is potentially one testable diagnostic of formation. So what else does turbulent fragmentation predict? The separation distribution of brown dwarfs formed in this fashion, at least from the largest simulations to date, scale with stellar host mass. So lower mass stars have closer in brown dwarf companions statistically. High mass stars have wider separation from dwarf companions. And then the brown dwarf companion frequency, the intrinsic frequency, at least in these large simulations by Matthew Bate and collaborators, are essentially independent of stellar host mass. So possibly another diagnostic. What about scattering?
Do people believe those simulations very much? I mean, are those simulations?
Ask someone else in the room.
Okay, go on, sorry.
Yeah. I think I'm an observer, and it's difficult for me to, I think, critique some of these in sort of a rigorous manner. I know there's a lot of complaints about the classic term magnetic fields and all these, right? And turbulence itself. They inject turbulence into sort of an initial sphere in hydrostatic equilibrium, and the amount of turbulence that they inject might affect the end result. So it's unclear if what we're seeing here, which seems to be consistent with the IMF from these simulations, would change dramatically with the different amounts of turbulence. There are a lot of tunable parameters, I think. But to first order, at least, it does mimic some of the observational properties of binary stars and brown dwarf companions. Okay, what does planet scattering predict? It predicts high eccentricities for a lower mass companion that's scattered out. It also predicts that there should be a scatterer much closer in. So potentially that's some form of diagnostic. And finally, if they're formed through core accretion at small separations, the metallicities of planets formed closer in and thrown out should be enriched. Okay, so that's a lot of theory about how these objects can form. What are the directly imaged planets that we know of today? There are really 5 that feel like planetary systems. There are a number of others, for example, that orbit brown dwarfs, but their formation is probably very different from these objects. So we have HR 8799, which was found in 2010 by Christian Marois and collaborators. Beta Pic B, which orbits inside of a warped inner disk. It was initially found in 2003. Not found, and then it came out on the other side and was confirmed. Fomalhaut, which is an odd system, is actually unclear if that's really a planet or not. HD 95086, this was found last year, and GJ 504 found from the Subaru Seeds program. So all of these companions and systems share something in common. They all orbit high mass stars, so A and a young G star, with masses between 1.2 to 2 solar masses. So that's great. So maybe that suggests the narrative that that I mentioned before, that more massive stars have more massive protoplanetary disks, fragment more often, you have more planets. The problem with that is it's unclear if this is a real trend or whether it's a selection effect. So this is a list of ongoing direct imaging surveys with more than 50 targets, and they go very deep. And you can see that almost all of them are focusing on this high mass stellar regime of A, F, and G stars for the most part. And there are a number of reasons for that. For one, they're much brighter stars, so it's much better for AO correction. And also you get potentially a feedback loop where the first directly imaged planets were found orbiting, say, Fomalhaut and HR 8799. And so a lot of groups are sort of biasing their surveys intentionally to find planets. But the problem is we need statistics to really sort all this out. So it's right now it's unclear if this is a real trend or maybe a selection effect. So what do we know about planets orbiting high mass stars in general? at small separations, we know that the frequency of gas giants is very large. It's very high. So these are the results from radial velocity surveys, like 20 years of RV baseline targeting almost 1,500 stars. It's a huge result from the California Planet Search Team, published by John Johnson in 2010. This is the planet fraction as a function of stellar host mass. The red curve shows a fit to the mass and metallicity of the host stars. And then when you marginalize out over metallicity, the blue line is the relationship between giant planet frequency and stellar host mass at small separations within 2.5 AU. So it's the frequency of gas giants scales roughly linearly with stellar host mass. For high mass stars, the frequency is very high. It's about 14%. Okay, go ahead.
If you go back, what's the red line is scaled as 10 to the 1.2 F? What is F?
F is Fe over H, I believe. Yeah. So it's a power loss scaling relationship. And again, when you marginalize out, the frequency as a function of stellar host mass goes roughly linearly. And then the dashed line here is predictions from core accretion models. So it's an uncannily good fit to the data.
What are the errors on the fraction? The dark black line, why are there so large errors there?
These are just Poisson errors. The sample size, it turns out it's very hard to get radial velocity.
Only few we're seeing, even though the fraction is high?
Yeah, so most of these surveys are targeting FGK stars, old FGK stars, so 0.9 to 1.5 solar masses. Fewer of them are actually targeting higher mass stars, but the trend does appear to be real. So what about at wide separations around high mass stars that we get from direct imaging? There are two key papers right now that are out on this. There's one by Arthur Vegan, that's part of the international IDPS, International Deep Planet Search, I think. So they targeted 42 A and F stars with masses between 1.5 to 3 solar masses. They found 1 brown dwarf and 4 planets in 2 systems. The problem is it becomes a little bit difficult to include, for example, beta Pic B in this, because there are environmental clues that there was a planet there, and so they went maybe deeper than they would have otherwise. There's a lot of sort of bias, and it's difficult to fold that into some of the statistics that you get out of it. But just taking that face value, the frequency that they get for greater than 3 Jupiter mass planets between 5 and 320 AU is about 9% with large error bars. And then for brown dwarfs, it's about 3%, likewise with relatively large uncertainties.
So you could add that number to the previous number to get the 1 percentage, plus you have a missing thing between that 1 and 5. So
yeah, so
is that the correct way of thinking about those numbers or not?
no, I think that is correct, except the RV results are for less than 2.5 AU, and then this is beyond essentially 5 AU.
Right. So you've got your 14% plus
Yep.
your 9% plus whatever you happen to be able to see in the middle.
Right. That's the idea. Yeah. And of course, there are caveats to all this in that these are different populations, different ages, etc. But a zeroth order, yeah. An even larger survey targeting A and B type stars as part of the Gemini Mickey planet finding campaign found no planets, 0 planets, 4 brown dwarfs in 3 systems. So from this larger survey, they get an upper limit that's characterized by this tongue plot. It looks like a tongue going down. So this is planet mass as a function of semi-major axis. So the way to read this is no more than, say, 5%, or let's say 10%, no more than 10% of A stars can host 10 Jupiter mass planets between these separations. So you sort of read it across like this and down. When you integrate this into a population analysis, the key results are that fewer than 20% of massive stars harbor greater than 4 Jupiter mass planets between 60 and 460 AU. Fewer than 10% harbor greater than 10 Jupiter mass companions between roughly the same semi-major axis range. The problem is that they took into account both the kinematics and metallicities of A stars and found that previous A star age determinations are probably underestimated. So I sort of hold this result as a little more reliable, both because of its sample size and a more precisely calibrated A-star age determination. So for the rest of this talk, I'll refer to these upper limits as really the best statistical result for high mass stars that we have.
What happened at 200 AU? Why is there like a continuity?
It's a good question. I think that has something to do with the models, interpolation of the models, rather than something maybe physical. But yeah, I'm not sure. All right, so that's basically the knowledge that we have about high mass stars. What do we know about low mass stars? Well, going back to the same plot, the frequency of gas giants is very low around low mass stars at small separations, roughly 3%. So we can plot this up in a planet mass semi-major axis cartoon. Now this is only for M dwarfs here. So the result at small separations is about 3%. So what happens if we go to lower planet masses, or more precisely, smaller planet radii, which we get from Kepler? Courtney Dressing and Dave Charbonneau answered this last year. The frequency of companions planets increases as you go to smaller planets. So all the way up to 40, even 50% for Earth-like planets around M dwarfs. That's small separations, less than 0.2 AU. As we march outward, microlensing answers this sort of intermediate separation range of about 1 to 10 AU. They found a frequency of about 17%. With large uncertainties, there are a lot of caveats associated with this. But what it does show is there appears to be a relatively substantial reservoir of gas giant planets around M dwarfs at these moderate separations. A more recent result by combining radio velocity surveys and direct imaging. So RVs probe the inside planet population, direct imaging together for the same targets probes the outside. Together they found a frequency of about 6.5% for gas giant planets, let's see, 1 to 13 Jupiter masses at less than 20 AU. Now, as of a few years ago, the best constraints purely from direct imaging were published by Eric Nielsen and Larry Close. They found that fewer than 50% of M dwarfs can harbor greater than 4 Jupiter mass planets between 10 and 200 AU. This is a pretty weak constraint out here. So to really make a dent into that, I started a program several years ago to target M dwarfs, so a direct imaging survey targeting low mass stars, which has a number of advantages. The first and foremost advantage of M dwarfs is that they're intrinsically faint. So if we're in a contrast-limited regime, we can probe much lower planet masses than we do for A stars. So for example, if you replace the HR 8799 host star, which is an A star, with an M dwarf, the relative contrast between the primary and the companions are more like 8 magnitudes instead of 12. So it's much easier to find them. Or equivalently, you can go and say to achieve the same limiting planet depths, you can integrate for a shorter amount of time. M dwarfs are on average closer, so a survey targeting M dwarfs will target smaller physical separations on average than for A stars. And finally, they're in general not accessible to the next generation of planet finding instruments, which require a lot of light. They have extreme AO systems. So GPI, for example, has a limiting magnitude of something like I-band of 10. So only the nearest M dwarfs are really accessible to that.
You use special equipment to block out the central star, or how do you?
Yeah, so you can have a completely opaque LEO chronograph or an apodized chronograph. In general, my survey is at Keck and Subaru. Subaru, with Haichao at least, has a completely opaque mass, which makes things difficult for photometric calibration and for image registration. Keck has a partly transparent set of chronographic spots that you can use with something like 7 magnitudes of extinction. So it's actually the perfect amount to be able to still see the star, register the images, and if you can measure the transparency of that mass, you can calibrate photometrically contrast curves and companions very well. So the targets for the survey were identified by my collaborator, Jenja Skolnick. She's been performing for the past several years a search for nearby active young M dwarfs. So cross-correlating proper motion catalogs with Rosat and Galax and then getting high-resolution spectroscopy to get radial velocities, parallactic distances, and matching these with young moving group, known young moving groups to identify new members of these groups, where we can leverage the age from the cluster itself. And these are all nearby. Distance is less than about 35 to 40 parsecs. Age is less than 300 megayears. So from that sample, after throwing out known visual binaries, in general, binarity is disruptive to giant planet formation. The timescales of circumbinary disks are much shorter for very close stellar binaries than they are for single stars. So let's get rid of all the binaries. We're left with about 122 young M dwarfs. Ages about 150 megayears. Typical distance of the sample is about 20 parsecs. So a third of these, after following up with imaging at Keck and Subaru, a third of them are close binaries of this remaining sample. So I'm working with a student, Ben Monte, who just moved from Caltech to the CFA to get dynamical masses for as many of these as we can. So we're doing orbit monitoring, doing spectroscopy, and we can test pre-made sequence models at the sort of intermediate age range of 10 to 100 megayears, really for the first time at low masses. But for the rest of the sample, 83 single M dwarfs, I got very deep imaging, 40 minutes per target. The technique is called angular differential imaging, in which you turn the telescope rotator off. So the speckle and diffraction pattern is stationary on the detector. And as the star undergoes sidereal motion, real objects, whether they be background stars or actual companions, will rotate through the speckle pattern. And then that way you can separate speckles, which look like planets, from real objects themselves. And then there's a post-processing procedure that you can use frames from any particular sequence to build up a PSF model and subtract it out, de-rotate everything, co-add it, and you get maps like this. This is a signal-to-noise map of one particular target, and out pops the candidate companion. So the typical contrasts that I'm achieving in the survey are about, well, for NURC2, 12 to 14 magnitudes at 1 arcsecond, which corresponds to sort of absolute magnitudes of 18 to 22. At the ages of the targets, this corresponds to limiting masses of about half a Jupiter mass to 4 Jupiter masses for the most part. So what do we find? A lot of point sources. Go ahead.
Can you go back to your PSF?
Yeah. This one?
Edge at 0.2 arcseconds, left side.
So this is, so this is combining unsaturated frames plus deep imaging. And I'm using the 600 milliarcsecond diameter chronograph, so it's 0.3 arcseconds. Yeah.
So that's the edge of the chronograph.
Yeah,
Thing point.
exactly. So I get unsaturated images and then deep imaging and combine the contrast curves together. Okay, a lot of candidate companions, 160 in the entire sample. So it turns out that about half the targets within this 10 by 10 arcsecond plus some rotation field of view, and of course it depends on galactic latitude. But the way we distinguish actual bound, gravitationally bound companions from background stars is by getting at least 2 epochs of astrometry. So we look at the separation and position angle, knowing the distance to the star and the proper motion. You can predict a background track. This is proper plus parallactic motion, so you get these wobbles in both separation and PA as a function of time. These are actual data points, so here's 1 epoch and the second epoch, and you can see it falls exactly on the background track. But you can also see the precision of our NURC2 astrometry is very good. So what do we find? No planets, but a couple of very interesting systems. So this is one in particular, which we thought initially might be sort of an HR8799E, the innermost companion, an analog to that. So it was a suspected member of the beta-PIC young moving group, the star itself, with an age of about 12, maybe 20 megayears. At those ages, and given the distance to the system, the companion mass would be about 11 Jupiter masses at 16 AU. So the problem is there hadn't been enough follow-up work in the literature on this star itself. So we got a high-resolution spectrum, and it turns out that the primary is a spectroscopic binary, which means that the activity, which was initially used as a proxy for youth and to flag it as potentially a young system, to kinematically associate with young moving groups was probably off. So it's unclear. We're continuing to monitor this, and it doesn't mean that it's not a member of this group, but there's a lot more work that needs to be done before we can make any claims. So we're continuing to monitor that. Outside of that, we have 4 brown dwarf companions with ages between about 10 and 120 megayears, masses of about 30 to 70 Jupiter masses. So 4 brown dwarfs in the survey, separations of about 5 all the way up to over 100 AU. They've all been spectroscopically confirmed. They show signs of sort of intermediate surface gravity, which is most noticeable in the shape and morphology of the H-band, which is sort of a conspiracy between collision-induced absorption and water opacity dependency on surface gravity. So the punchline is that young planets and young brown dwarfs have very peaky H-bands, very angular H-band shapes. Old ones are much less so and have a very strong notch carved out by iron hydride. So all of these systems show sort of intermediate signs of surface gravity, which is consistent with the ages of the primaries. Here's just another example. In this particular one, we have lithium absorption, H-alpha emission. This is in the companion. And again, sort of an angular morphology to the H-band shape. And so nothing terribly surprising there. So what do we get statistically from this? So to incorporate 83 single stars, 4 brown dwarfs, 0 planets, to get some kind of robust answer about the population of planets around them dwarfs, we have to incorporate the ages, the distances to the stars themselves, uncertainties associated with that, contrasts, non-uniform field of view coverage. So we have, for example, uniform 100% field of view coverage up to some separation, and then that dies down because we have some both rotation and finite field of view. We have to take into account wide binaries, which can dynamically carve out some region where planets shouldn't exist on long orbits, or on long timescales in stable orbits, and also which evolutionary models should be used. So I'll skip through some of this, or go quickly through it. But I think the most important point is that the choice of evolutionary models has really the largest effect on the answer. So what I mean by that is the models, for example, that I showed on like slide 2, those are so-called hot start evolutionary models. Those assume that the initial radii at t equals 0 are essentially infinite. These objects collapse down and simply convert their potential energy into heat and radiation and just cool uniformly over time. Now that might not be a realistic treatment of the formation of these systems. If, for example, through core accretion, you have a core that reaches about 10 to 20 Earth masses and starts accreting gas to form an envelope, which becomes a giant planet, you get dramatic losses of energy and initial entropy from these accretion streams in the form of accretion luminosity. So you can start much lower and simply evolve these over time. This has the biggest impact on the statistical results. The way this is done is simply through a Monte Carlo analysis of random orbits, using these evolutionary models and all the parameters of the stars and our contrast curves. We do this for each point in companion mass in semi-major axis space to build up a sensitivity map. So here we have, for one particular example, this shows that we're, for example, 90% sensitive to planets with these masses in these semi-major axes, and essentially not sensitive because of the wide field of view coverage here, and then the contrast at small separations. So we get these sort of characteristic curves like this for every single target. And you can see that the sensitivity is much lower for these cold start cases. You're essentially bringing up the sensitivity. But it's not substantially worse. It's maybe a Jupiter to a couple Jupiter masses difference in sensitivity. So when we integrate over both semi-major axis and planet mass, we have to assume some form for the underlying population of planets. If we assume, say, a logarithmically flat distribution, it turns out the answer doesn't change that much if you alter that a bit. We get the following, which is really the punchline. So we have upper limits, 95 percentile upper limits on the frequency of gas giants for, between 10 and 100 AU around M dwarfs. So at most, 10% of M dwarfs can harbor 1 to 13 Jupiter mass planets. and at most 6% of M dwarfs can harbor 5 to 13 Jupiter mass planets in this semi-major axis range. And those upper limits are about 50% worse, up to 15%, about 9% in the cold start scenario. So we can play the same game with our brown dwarf companions, except those are found in projected separation, which corresponds to a distribution in semi-major axis space. But applying the same sort of idea to our brown dwarf detections, we arrive at a frequency of about 3%, plus or minus 1 or 2%, for the frequency of brown dwarfs between 10 and 100 AU around M dwarfs. OK, so we can go back to our plot here. We can fill in our upper limits. And really, if you take a step back, you can sort of see that at small separations, the frequency is rather low. It might increase a bit, at least for microlensing results. And then these are upper limits at wide separations. So what we can say is that, well, first of all, there's no evidence as of now, because the two largest studies targeting high mass stars and low mass stars are really just provide upper limits on the frequencies of gas giants at wide separations. There's currently no evidence for any sort of stellar mass dependency of giant planets or any stellar mass dependency of wide separation planets. So despite all directly imaged planets being found around A stars, there's no statistical evidence that that's a bona fide trend. It doesn't mean it doesn't exist, but there's no evidence for it yet. We can also say that there's no evidence for a stellar mass dependency of wide separation brown dwarfs. The frequency seems to be about 3% across all stellar host masses. And finally, because we probe sort of the region where disk instability, if it operates, should produce planets around the most common type of stars, we can say that overall, compared to core accretion, it doesn't appear to be a particularly common mechanism for forming gas giants. OK, so where do we go from here? The punchline is that for small separations, we have this very well-described correlation between planet frequency and stellar host mass, from which we can infer something about planet formation. At wide separations, this is what we're dealing with, is upper limits. So what we really need are samples in the hundreds to distinguish very small differences in these intrinsic frequencies. So for example, if AFG stars have intrinsic frequencies of about 3% and maybe about 1% for M dwarfs, you need a sample size in the hundreds, maybe about 500, to detect any sort of statistical difference at the 2 sigma level. Now, ongoing surveys are going to produce these sort of precise results around high mass stars, but what we need is sort of an equivalent survey around low mass stars. This also corresponds to a time when there are now hundreds of newly identified members of the low mass members of these young moving groups. So here's just a sample from the literature from 2012 to 2014. And really, the number is increasing so that we now have about 300 or so just over the past few years. I'm also conducting my own survey for these low-mass members of young moving groups by cross-correlating large catalogs of bright M dwarfs, starting with sample sizes of something like 10,000, cross-correlating them with Rostat and Gallic surveys, pick out the active ones, which are proxies for youth, and then perform kinematic analyses by defining UVWs with those of known associations and comparing the predicted proper motions to the measured proper motions, marginalizing out over radial velocity and distance. The punchline is that I've identified about 130 known or suspected young moving group members and found another 200 to 300 from this work. So we're following up both with RoboAO on the 60-inch at Palomar, which has an AO system that's based off a UV Rayleigh scattered laser. So we get AO correction in the optical. It's a small telescope, but it's a way to identify binaries and get the binaries from this program before following up with imaging. And we've already gotten over 250 of these. And we're also following up with optical spectroscopy, low and high resolution. These are otherwise anonymous M dwarfs. So spectral types, spectroscopic signs of youth, and radial velocities to confirm membership for many of these. So the notion behind the program is, instead of going very deep for a relatively small sample size, with only 5 minutes of integration, we can actually get down to planetary masses because these targets are faint. So expanding the program, essentially a snapshot survey, but for 500 targets. And we can do this because if you look at the relative contrast in H-band as a function of planet mass for an A0 host star and an M0 host star, integrating at with only 5 minutes at Keck, say with NERC2, at 1 arcsecond, already gets you to the planetary mass regime for essentially young ages. Going down 1 or even 2 magnitudes fainter by integrating much deeper really doesn't buy you that much more, at least for an M-dwarf host star. For an A star, it does because you're in the substellar regime. So 1 or 2 magnitudes buys you essentially tens of Jupiter masses of limiting planet depth. So for M-dwarfs, we can actually get away with this snapshot mode survey. And here's just another example using real data for an actual data pick young moving group member. 5 minutes of data with PSF subtraction using a reference PSF library versus 40 minutes. You can see the difference in our sensitivity maps. It looks substantial because it's on a logarithmic scale, but this is really only a Jupiter mass or so. So already, having imaged only a few dozen targets so far, we found something very interesting. It's a companion at about 50 AU with a mass of about 13 Jupiter masses. It also has very red, near-infrared colors, and really sort of bridges the gap in terms of its atmospheric properties between warm, dust-free planets like Beta Pig B and much colder, peculiar planets like HR 799 and 2MASS 1207b, which is a companion to a brown dwarf. And again, you can see that the shape of its H-band is much more consistent with its angular youth compared to older field objects. And finally, I'm coordinating proposals in Chile and at the CFA, and through ESO time, basically continue this palm survey in the south. Most young moving group members are in the southern hemisphere, so this is natural extension to the south. My collaborators here are Lucas Chiesa, Jennifer Yee, Larry Close using Magellan adaptive optics, Dimitri Mowat, Sasha Hinckley, and Adam Kraus with VLT. And so I'll leave you just with 2 slides of where I hope the field will be in not too far. So in the near future, what we'd like to have are intrinsic frequencies, giant planets measured at the level of, say, 0.5% or percent with these large sample sizes. Maybe we'll find a correlation between solar host mass and stellar and giant planet frequency. Maybe we won't. If we do, that would suggest disk instability is actually the formation mechanism. But this will be very interesting to make these comparisons. And finally, in the not too distant future, it's only, 8 years away, we're going to have 2, maybe 3, probably 3, 30-meter telescopes, which will carve out the statistics of planets in the 3 to 10 AU range, in the 0.5 to 5 Jupiter mass range, and JWST, of course, will help in this endeavor. Okay, I'll leave you with that future notion. Thanks.
Any questions?
So I was wondering, is there any correlation between mass and eccentricity? How well can you measure eccentricity of these orbits?
Not well at all. Yeah. So the problem is that the timescales, the periods at, say, 100 AU are thousands of years.
Oh,
Hundreds of years.
The exoplanets, but if you come to the...
Oh, small separations.
Yes.
So small separations, that's a good question. There's a non-negligible population of non-zero eccentricity planets, but I don't know how that correlates with, say, planet mass or stellar host mass. It's a very good question. Yeah. It would be simple to go to one of these catalogs where they catalog all of the known planets, exoplanets.eu, and there's a US version as well, and simply plot it up and see what the answer is. That's a good question. Yeah. But that could potentially inform some sort of scattering scenario, or at least constrain that as being, if, for example, there's a correlation with planet eccentricities and stellar host mass, I guess that would suggest that more planets, we know that the intrinsic frequency is higher around high mass stars, so maybe dynamical interactions would also occur more frequently. yeah, I don't know.
I have a question here. The follow-up of the Young's objects. You've followed up now 50 of these
So for the young,
for the snapshot survey.
yeah, well, it's 50 out of, yeah, so it was sort of a pilot study intended for this much larger program that I've proposed for.
So what fraction of those have you been able to confirm are actually young? All of them? Or?
Essentially all of them. It's from the Muller list.
Okay.
Yeah. So we've found a couple brown dwarfs in there, and one interesting companion, maybe the tail end of brown dwarf formation, but the caveat to this companion is there's this degeneracy between the mass. So just taking at face value the luminosity of this companion and the age, it's just in this region where you have overlapping mass tracks. So it could be 13, it could also be 25 Jupiter masses. And that really hasn't been taken into account in any direct imaging surveys at all, period. So it's a complicated game. And we're, I think, at the beginning, observationally, of constraining this outer architecture. But we have to be very careful. There are a lot of caveats to all this stuff.
I think it's amazing that not much over 100 years ago, a elderly scientist said we would never know what the distant stars are made of. Now we're starting to figure out what the planets are made of.
Yeah. Well, that's a whole nother talk.